Welcome, everyone. It's my great pleasure to introduce our distinguished speaker, Professor Mark Cutkosky today. He came all the way from California for my PhD defense 2 days ago and is now sharing his expertise with us. Mark serves as a Fletcher Jones professor at the Department of Mechanical Engineering at Stanford University since joining Stanford in 1985. Prior to Stanford, he worked at the Robotics Institute at Carnegie Mellon University, where he received his PhD from. And he was a design engineer at Alcoa in Pittsburgh. Mark is renowned for his groundbreaking research on robotic manipulation, tactile sensing, and the design and fabrication of biologically inspired robots. His work continues to push boundaries of what's possible in the field of robotics and mechanical engineering. And please join me in welcoming Professor Mark Cutkosky.
Thank you for the very kind introduction. It's great to have just a packed room here with a lot of distinguished people and a lot of very good students to talk to. I thought what it would be interesting to talk about today is a joint project that we just finished with NASA. My collaborator on this has been Professor Marco Pavone in the Aero and Astro Department, and the other co-investigator is Mathieu Laporte. He's a geophysics professor at Stanford, and then of course the students who really do all the work are listed at the bottom. In particular, I'll be talking about some of the work of Tony Chen, who graduated about a year ago. He's now at Harvard doing a postdoc, and he'll start as an assistant professor at Georgia Tech in the fall. And one of the other students whose work I'll be showing is Julia. I'm right now reading her thesis. She just is defending. And then Stanley Wang's a new student, and Dan Morton is a new student with Marco. So the motivation for this project was that there are places, especially on Mars, that are particularly interesting to explore and also just extremely difficult. Oh, yeah, it's a little bright maybe. Oh, perfect. Yeah, maybe for videos, it's going to help. Yeah. These include caves and they include lava tubes on Mars. It turns out there's also lava tubes on the moon, and we'll talk about that later because the chances of doing anything on the moon in the near future are much better than they are on Mars, I think. In particular, these are lava tubes. It's hypothesized that if we would want to see signs of past life inside a lava tube might be a very good place to do it. They're relatively shielded. They're shielded from radiation. They're shielded from extremes in temperature, and better at preserving the remains of life. Also, it's been pointed out that if, yeah, this has been happening. I think it will come back on again in a sec. I'm not sure why it. There we go. That if we will eventually have any human habitation, inside a lava tube is a great place to try to do it. Once again, because you're relatively shielded from radiation, you have a more stable thermal environment. And so if you erect a structure inside a lava tube is a place of great interest. Okay, so that's the motivation. Now, the problem with lava tubes is that they look like this. These are, this is one in the Mojave Desert. And we don't know for sure whether the lava tubes on Mars have the same kind of very rough, rocky terrain, but we suspect they do. And then the question is, well, before any kind of people will go into these places, we're going to need robots to explore them, to set up a bit of infrastructure. What kind of robot is suitable for this terrain? The Ingenuity flyer on Mars was amazing. Amazing what it can do, but flying inside a lava tube is another matter. And also, especially in that incredibly thin atmosphere, you can't apply any force. So it's hard to do any work. Legged locomotion in this kind of terrain is difficult for people, and I think also for ANYMal and other quadrupeds. And not only that, but you don't just want to sort of clamber over the ground. You want to be able to look at the walls and ceiling, because that's where it's likely that you're going to find some interesting chemicals and evidence of past life. So there have been climbing robots worked on at JPL by some of my former students. This is one with Aaron Parness that's called Lemur. This is Lemur 3, I think, using microspines to climb a cliff face. And the problem is that if you have a robot of reasonable size that you could fly up to the moon or to Mars, it isn't all that big. And so the world then becomes full of very large obstacles that you have to navigate around and clamber over. And one way to make yourself work better in very rough terrain is to say, well, let's just make the whole robot bigger. The bigger you are, the smaller the obstacles are. Unfortunately, it doesn't scale very well with payload. Your weight grows rapidly, and just the whole cost of the mission becomes large. So our idea was, well, what if you could have a small robot, something the size of a carry-on luggage suitcase, but with really long reach? So imagine a suitcase-sized robot where I could reach up to that projector up there. And the best concept, the best illustration of the idea is from this GIF by Stephanie Nudik. And so I'll just play it, and you get the idea right away. So now it's making its way down to the lava tube floor. Which, remember, is very rough. And I think it concludes by taking a selfie. Yes, there we go. So that is the basic idea. And, you know, I'm a Bioinspired robot guy. So this presents a bit of a paradox, because why, you know, I like to think about Bioinspired design, but why should Bioinspired design be at all useful for space robots? There are, as far as we know, no biological creatures in space. And why would anything that they've acquired from evolution on Earth be relevant? Good point. Nonetheless, it's hard not to think about it. And the idea of having a small robot with very long limbs, the first place you might say is, well, are there, in fact, creatures on Earth? Sorry, it'll come back again in a minute. I'm not sure why it's, I don't know. I think it just, maybe I'm just not going through slides fast enough. I don't know. Anyway, so there are these insects, the harvestmen, where you have a very small body, very long limbs. It, in fact, allows them to work very well in extremely complex and three-dimensional terrain. But as you think about it, these are all very small on Earth. And the limbs are really not strong. They're not able to apply large forces. It doesn't seem to scale well. We don't have anything with this morphology at the kind of scale that I'm talking about, right? So think about that. The other point is that the limbs in bending are not strong. However, it's interesting what these insects actually do is if there's going to be a thunderstorm or something like that, they spread out. These limbs are much stronger in tension than they are in bending. So they do this spread-eagled posture, and they're able to ride out the storm. But it doesn't scale well. Beam strength goes as length squared, mass goes as length cubed, and that presents some problems. Then again, if gravity is not an issue, maybe you could scale to the kind of scale that we're talking about. So this is the Japanese spider crab, and it's actually getting to be about the size of the ReachBot prototype that we built. But also just notice before, because I'll come back to this later, what's at the end of the limb there? You see the gripper, yeah. Okay, so I could make jointed limbs, and it gets kind of long and complicated. We're talking about a robot with many degrees of freedom. And if I say, well, look, what I really want is a very long reach, what's the simplest possible structure that I could use to do that? And there I can take advantage of these unrolling boom structures that are used for antennas and solar sails and things like that in space. This is a carbon fiber boom. You can imagine it's like a tape measure. It rolls up and you extend it out. And there's different kinds and different weight and strength ratios, but that's what we're using to make the limbs. The other principle that we want to keep in mind is that if you want to do a good job of navigating in these very complicated three-dimensional environments, it also helps to have the ability to do a strong grasp at the end of each limb. And for example, like this orangutan here. Okay, so if we do that, part of what attracted me to this whole concept at the beginning is that it allows me to bring back grasping, which is something that I've been interested in for 35 years. If you have a small robot with multiple long limbs, you basically turn locomotion into a grasping problem. So there's a whole big long body of theory about grasping. You have multiple fingers, each one is a serial chain. Together they work in parallel. They apply forces to a body. You can talk about metrics of grasp stability. You can use it for control. And remember that what's interesting about these fingers is that they can push upon the object, but they can't pull. So there's an interesting unisense force constraint. And we have basically the same kind of thing. Only now, because these booms are very long, they can apply much more force and tension than they can in compression or bending. So to a first approximation, we have sort of inverse fingers that can pull but not push. And so a lot of the mathematics of grasping and so on carries right over. What we really have is that at each of these booms, it has one long prismatic degree of freedom, and then it has 2 rotary degrees of freedom at the base, and then 3 passive degrees of freedom out at the tip. And the one part that's a bit different is the constraints at the end. In grasp theory, we talk about how fingers, they can push upon an object, but the force that you apply, of course, is subject to the constraint of Coulomb friction. So you talk about the force vector should be inside the friction cone. Here, the contact constraints are somewhat different, and I'm going to spend the next few slides going into that in a little more detail. Well, for grasping rock, our solution, of course, is to use microspines. We love microspines. We've used them for over 20 years. We use them with Boston Dynamics on the RISE robot. We use them with JPL on Lemur, and so on. And so I need to give you a sort of very quick crash course on spines. The spines are literally sharp little, we've used various things. We've used suture needles, we've used various kinds. Actually, our favorite thing nowadays is to use Japanese microfish. I think it's wonderful, by the way, that Japan, the country that has bonsai, also has a hobby of microfishing. And they make really good microfish hooks. And so we clip those and we put those into our spine suspensions, and each spine, if you would look at it with a microscope, and these are things with about a 10 micrometer tip radius, interacts with the rock surface. And depending upon how rough the surface is, you have a certain probability of finding what we call an asperity, which is a little bump or a pit within a certain unit of area. Okay, and then having latched onto an asperity, how much force I can apply and in what direction is a function of the local angle of inclination, it's a function of my approach direction, and of the local coefficient of friction. So if I have some probability distribution that describes the surface and how rough it is and how many features there are of certain angle per certain unit area, I can make a probabilistic prediction about forces that spine can apply, okay? But it is stochastic. And then if I have many spines, I can add that up. Well, only if I assume the spines are independent. And we'll come back to that later, because that leads to a whole problem of spine suspension design, is to make sure that when you have 5 spines, do you really get something approaching 5 times more force than just 1 spine? And a big practical design consideration. So spine theory up on the left, where the models actually work very well. They're able to predict mean spine forces very well, but it is stochastic. There is a fair amount of inherent variability. So it's like saying that there's a 70% chance that it will rain tomorrow. And we use that, and then we use that to think about the grasp. So we have a gripper in the current version of RISE. It's a 3-fingered gripper. It doesn't have to be 3, but 3 actually works pretty well. And what I'm doing is that I'm solving for the quality of the grasp. So I have force equilibrium equations. I have an addition, it's a little bit conservative, but I also want to be sure that when I pull on the gripper, that all the fingers remain in contact, that one of them doesn't pop off. It actually could possibly still hold with 2, but then I have less stability. So we enforce that constraint as well. And then I want to have load sharing among the fingers. And if I do that, I get a set of equations that I can solve such that given some force applied to my compliant wrist, I can predict what the force will be at each finger, and then I can ask whether the force at each finger should be sustained by the collection of spines on that finger. Does that make sense? So we're almost done with grasp theory here. So I'm just going to stop and take any questions on that before moving on to other things.
The arrangements of how the spines on each individual finger?
Yeah, I will talk about that a little bit in the next couple of slides. Yes. How many spines and where they should be. Yeah. Other questions? So I know you got a bunch of people working on dexterous hands. This is grasp theory. You should be, imagine if your hands, like the ones I saw this morning, imagine if you had microspines on all the fingers. You could have almost no motor torque at all and still hold practically anything. Yeah, go ahead, Ardian.
What is the role of compliance?
Yeah, so this is a very much under-actuated gripper. We're not trying to manipulate with it. So we have a large amount of under-actuation, and then we also have physical compliance. And I will show you that in the design in the next few slides.
Question on Zoom.
Yeah.
Saying how efficient a soft gripper would be than using spines.
I think not nearly as efficient. Soft gripper, in the end, I'm limited by friction. And a really good frictional surface, you could approach a coefficient of friction of perhaps 1 or so. With spines, on a rough stone wall, I can hang my entire weight. Well, there's no normal force, so the coefficient of friction is, I guess, infinity. But yeah, I can do easily tens or even well over 100 kilograms with enough spines. So I don't actually think a soft gripper will work as well. Good question though. Other questions? Take one. Okay. So we apply a pull force. And so what we're doing now, what we're eventually going to do is build the analog. Remember, I talked with grasping, you say forces have to be within the Coulomb friction cone. I need to build an analog to that. It's called a limit surface. It, in general, could have up to 6 degrees of freedom. It's a convex surface. And the way we do it is like this. We assume a grasp, and then we apply forces at the wrist. And we solve the grasp equations, and we get the forces at each finger, and then we check whether all the fingers have forces that they, in theory, can sustain. And if they can, we increase the force a little more until one of them can't. And as soon as I get a failure, I record 1 point. And so we do that as a Monte Carlo simulation, and thereby we gradually build up a limit surface, which looks like this. So because I've assumed a compliant wrist, with no torques, if I embed a coordinate system there, I can plot a 3-dimensional limit surfaces. So I can embed a coordinate system at the wrist, forces in X and Y and Z. It's a convex surface. And if you take a cross section of it, it looks like what we see on the left here. So remember, it was stochastic. So I have my predicted mean, which is in blue, and then 1 standard deviation in red. And the idea is that if I apply a force, I want that force to be inside this limit surface. If it is, then in theory, I should be able to sustain that grasp. I'm going to use that information for planning later. And if I'm conservative, maybe I'll use the lower red boundary. And you might be asking, well, what are these funny flat faces here on the sides, which you can see here as flat facets here. And remember I said earlier that I was imposing the constraint that when I pull, none of the fingers should pop off and leave me with just two. So that's what makes those facets. That makes sense? So we build this limit surface, and it already begins to tell us some things. We're going to use it for motion planning, for grass planning. It also gives us some insights into gripper design. Well, there's another cross-section that I've plotted. And as you can see, not too surprisingly, if I increase my internal grass force on the gripper, then my maximum pull force increases almost, essentially linearly, okay? Well, suppose I want to sustain a large force, and I really, with my gripper, because I'm very much weight limited, I have this long arm that I'm putting all the way out. I'd like the gripper to be very lightweight, as low inertia as possible, actually. And therefore, I'm going to use small motors and so on. So suppose I can't actually afford to exert 12 newtons worth of internal grass force, and yet I still want a really strong grasp. What could I do? Well, more spines. Remember, if I have enough spines, I can hang my own weight from it, provided I maintain independence. And in fact, with our current spine suspension, what you see is this, that as I go from, on one finger, as I go from, say, 10 to 20 spines, I'm getting a substantial increase in my pull force. And as I go to a higher number of spines, I start getting diminishing returns. And in fact, 50 is really not much better than 40. And that's because it's actually pretty hard to have increasing numbers of spines and still have them all be completely independent of each other. A couple of other things that you learn. One is, it really helps. This is very different from when we were doing climbing walls. Here we have the option to look for features that we think are kind of graspable. And that makes, again, a big difference. So this angle alpha, it essentially is related to how much I'm able to enclose a part of the surface. So the worst case, which is a flat wall, is this light blue line down at the bottom. And what I'm plotting here is the ratio of pull force, maximum load force that I can apply to my internal grass force. And as you can see, as I increase the grass force, it doesn't really, I don't get very much, the pull force just increases, directly. On the other hand, if I'm able to get to wrap around surfaces a little bit, I can get much, much larger ratios of pull force. Although again, eventually it doesn't help anymore. So if I can wrap my fingers partly around a knob-shaped object, that helps a great deal. But if I am to the point where they're just opposed to each other, it isn't really actually much better, which again, it kind of makes sense, I think, intuitively. And finally, if I'm going to wrap around these features, what kind of finger design should I have? How many phalanges should my fingers have? How many degrees of freedom should they have? And this is a problem of conformation. So what we're trying to do is conform to the surface at multiple length scales. At the microspine level, I want to make sure that all of my microspines, even on a very rough surface, are still able to reach the surface and find asperities and sustain some load. I want the finger to conform to the surface at its length scale, and then I want the whole gripper to be able to conform to surfaces. So we did a study, a numerical study, for example, on the finger to sort of ask ourselves, how many degrees of freedom should the fingers have? 1 or 2 or 3 or 4, or even the worst case here down is 5, where I have the ball joints, and then I've actually made the spine suspension have a linear degree of freedom at the tip. And what's plotted on the right, each color represents the amount of additional area over the previous case. And so what we found, in fact, is that having this extra final linear degree of freedom actually made a substantial difference. I was able to get substantially better coverage and conformation to the surface. So here's the gripper, and this is especially Tony Chen's design. It is a under-actuated gripper. It is just meant to grasp. It doesn't manipulate. I assume it will come back in a minute. There we go. It's a 3-fingered gripper. Everything is driven by one tiny motor and huge gear ratio. Honestly, I kind of think in retrospect that Tony could have afforded a slightly bigger motor. But what it mostly does is it makes the hand very slow to close. There are tendons routed through these fingers. There's a differential that does load sharing between the fingers. And then here are the spine tiles, and I'll say a little bit more about them in the next slide or so. So one way to do load sharing, of course, is to use a differential. It's a very old idea going back to Roman, maybe even pre-Roman times. If you have several horses or oxen pulling a heavy load, you don't want the one that gets a little bit ahead of the others to wind up taking all the force. And so you set up one of these kind of differentials, and we do that too. So here is the design, and I'll spend just a moment or two going through some of the features of it here. It's a busy slide. The differential is up in the upper right corner here. Let me move my thing. So the motor is pulling on that and loading the 3 fingers through the differential. The spines down at the tip, these are what we call the linear spine array. Okay, so there's a bit of a history there. When we started working on spines and we understood this need that every spine should be able to load independently of its neighbors, we actually made a compliant 2-material suspension for every spine. When you look at things like the Rise robot or early stuff, and that works, it's actually great, but it leads to a kind of a large apparatus. The one where there's a photograph of me hanging on a wall, the spine array is as large as a tennis racket. What we discovered is that if we do these spines that are sliding linearly, we can get a much denser array. They do not do load sharing as well, but they more than make up for it in terms of higher spine density. So if I want to do kilograms, tens of kilograms, or maybe hundreds of kilograms, we mostly have been using these linear spine arrays now. And then we have tendon routing with compliance. You were asking about compliance, Robert. Yes, there's compliance everywhere in this system, because what I want the hand to do is that if I just push it at the end of my long boom, which is extending, it should just adapt to whatever that surface is in a compliant way, and then I tighten the motor to get a good grip. And that's how it works. And yeah, I think that's as much as I really want to say about the motor right now. Let me take questions on this, though, before I move on, especially the hand design people. Yes, please. Yes. What it had to, okay, so the plot I showed where you get sort of diminishing returns, so going from 10 to 20 spines and 20 to 30, 40, 50, that was specifically for these spine tiles. So the tile right now has, I don't know, they look to me like they have about 20 or 30 spines on them, and there's 2 of them, each on its own little compliant suspension. So that was data for these particular linear spine arrays, okay, which don't have perfect load sharing. If I go for the one where the spines are actually, each spine has its own 2-axis suspension system, and it's the much bulkier array, then the load sharing goes almost linearly with increasing number of spines. It's just it leads to a sort of very large apparatus. Yeah. In theory, it shouldn't, because I'm assuming that asperities have like a Poisson distribution over the surface, okay? And so each spine, independently of its neighbors, has a finite probability of finding an asperity within within its range of motion. So, okay, so I mean, eventually it will matter if I pack them so tightly that they can't find a very large area, you know, then my probability goes down, but yeah. Yeah. I think Arden was next, and then you and then Thomas, yeah.
What's the isotropic properties of spines yielding distal to proximal?
It's highly anisotropic, and we're banking on that. So when we're climbing, we know that the main load is downward. So the spines actually, if you will push, they slide upwards quite easily. It's almost like a ratchet. And from side to side, they're pretty good. It's maybe 75% of the downward. But that also, what that influences is this kind of what angle do I want the spine to be fixed at, and what angle do I want it to approach the surface? And again, you can go through this whole numerical analysis and sort of come up with what you think is an optimal number. And I mean, is anybody here a bike enthusiast? Elliot Hawks, who's a former student now at Santa Barbara, he was seriously looking at putting spines on his bike tires so he could go around corners faster. Yeah, yeah, there was some discussion, yeah. Sorry, Thomas, I'll get you next, yeah. Go ahead, yeah.
To the spring, that helps
Yeah.
you to actually deal with some of the impact that happens to the needles.
On the spine, yeah.
But what happens if you get a dulling of?
You do get some dulling, and it matters. The number of asperities I will find per unit area is a function of the spine tip radius and the surface roughness. Okay, and so what happens is that we immediately get a bit of dulling, and we sort of plan on that, and then it stabilizes. However, and this is a problem, is that if you would in order to write papers, limit surfaces and proving that your models are correct and all, you have to load stuff to failure, right? And that absolutely, you know, meaning that you load the grip until it slips or fails. And that's really hard on the spines. So what we tend to do are these numerical plots where we have a few data points that that show that that it matched. And then you have to put new spines in, yeah. So practically speaking, what it means is don't load them to failure. If you have a good limit surface, and this is part of why the limit surface is important, and then I never load it to more than 75% of what I think it should be able to sustain, then they last a long time.
What you have here with the spring and the back push, and you have an overloading intermediate rigid sort of pickup surface that could be not.
Oh, like a frictional overload? Yeah. Well, interestingly, that's what we did for a different gripper called the Bear Paw that was for RoboSimian, which is this rather heavy robot out of JPL. It's 100 kilograms. And what you're describing is kind of what we were doing for that. For this, we're not applying quite such large loads. So grasping with spines, actually, it seems to work quite well.
Because
Yeah.
once you have mass, you have to have somewhere a safety on it.
Yeah, yeah, and you may need a spare hand or two, or something, yeah. Yeah, Thomas. Yeah, no, it doesn't help. In fact, no, because the act of loading, actually, there is a little bit of small scale vibration as the spines independently settle on asperities. But yeah, good, interesting question though, yeah. We did actually, yeah. So afterwards, we'll take a look at this Bear Paw design. It had granular jamming palm. It had spines, and the whole idea was to really handle these huge loads from RoboSimian climbing a cliff. They were there was a palm with a granular media and spines embedded in the granular media, and then we would pull back, and it would load. It doesn't load share quite as well as this mechanism, but it's actually still quite good and very durable. Yeah. Oh my gosh, yes.
So assuming that spine radius is inversely proportional to asperities available, how do you then choose the right spine size.
Yeah,
Don't
so it
almost
depends.
cover.
Yeah, so this is interesting. It depends on how rough the surface is. And so this was sort of an early, this is old stuff, but this was an early insight with the climbing with the Rise robot. Because you look at like a squirrel and then a cat and then a bear, and the claws are getting bigger and bigger. And so, you know, the Rise robot was pretty heavy. It was about 20 kilograms. So should it have a sort of raccoon or, you know, bear-sized claws? No. The spine size should depend on whether I'm climbing cement or stucco or, in this case, lava. And it's just how many spines then I need. Yeah. Yeah.
This appears to be highly underactuated.
It is completely underactuated, one actuator. Yep. Yes. Yeah, because you need it to stabilize, you need it to be stable while you're putting it out on the arm. So there's a centered location, or yeah, an equilibrium position. Yeah, no, that was more just sort of rule of thumb. You know, we're using compliant materials. If it's too stiff, then you start to get imperfect load sharing. If it's too soft, then it's too wobbly as it goes out on the arm. Yeah, there was nothing very profound there. Yeah. Yeah. Mm. Pretty tight, because otherwise you get dirt particles in there and they jam. And actually a better solution for terrestrial applications is to not use springs, but to use pneumatics. Blowing, it means that all the spines it's like a constant force spring, first of all, which is better than a linear spring. Secondly, it keeps it keeps dust particles out. So it's, we actually, there's a paper on this in IJRR, International Journal of Robotics Research, where we explicitly, yes, we're depending on a little bit of play in order to get some of the load sharing, yeah. Yeah.
So, because you talked about pneumatics just now, I was thinking, right now it's linearly constrained along this axis, and the spine can move up and down.
Right, and then there's a little bit of lateral play.
It's a pneumatically active system. How would you talk about it? What if there's a soft surface where you can maybe only vary a little bit in length, but you can actually conform around the surface better? And then the surface where the spine is mounted itself is a more conforming.
Yeah, I mean, that's the same thing that he was asking about. Like, what if I had a jamming medium palm with spines embedded? And we've done that, but not on this robot. Yeah, it's good. It's a good idea, though. Yeah. Okay. Yeah.
How often can the spine arrangement can be used, or what is the general lifetime?
Yeah, the lifetime is, we haven't really tested that too much with these robots. It's certainly many hours, which does mean that if you will, and what happens? Eventually they get gradually more and more dull, which means that gradually they'll find fewer asperities per unit area. And I start relying more on the, large scale geometry, grasping to get enough force. It is a concern. Probably if you will send a robot up to Mars, it should have some, it must have spare spines and spare hands. What we learned early on with Boston Dynamics and the Rise robot is that the secret really is not to load grasps to failure. And I mean, I remember horrible days when the guys from, before they had good force control, they eventually put 3-axis force sensor on every foot of the 6-legged Rise robot. And before they had that, they were calling us, it was terrible. It was like every 2 days, it's like, oh, we need 200 more spines. And the grad students, of course, were like, wait a minute, we're not in the business of providing, large quantities of spines to Boston Dynamics. So 2 things. One was teaching Boston Dynamics how to make their own spine suspensions. And secondly, do force control. Yeah. Yeah, and so we do that. I want to move on now and talk a little bit about a couple other parts of the problem. This is Julia's work especially. There's an interesting perception problem. In contrast to what we did with the earlier climbing robots, like the Rise robot, where I'm just climbing a more or less featureless wall, Here I'm relying on finding features in my vicinity that look like they would be good to hold on to, like that cornice up there. And so there's a kind of a two-stage perception problem. One is before you send an arm out, you're looking around with cameras on the body to see if you can identify crevices or knobs that look like they would be good to hold on to. And then as you extend the arm out and you get within a meter from the surface, now we can look at it in much more detail, see is it really as rough as I was hoping it was, and is there really a good place to find the local surface. So this is so she's using nothing special here. It's an Intel RealSense camera and time of flight also, but and identifying spaces where we think that there's interesting curvature at the length scale of the gripper in order to take a grasp. And remember, from a few slides ago, I showed that plot of wrap angle versus pull versus internal force. And so that's what I'm looking for. I'm looking for things where I think I'm going to be up here in this regime and not down here. As you get closer, of course, you can see a lot more. And you can, this is, by the way, that's a great graspable feature there. Use that to do your final grasp planning. So it was a spring of 2023. Tony and Julia and Stephanie took a field trip to the Mojave Desert. The geologists told us that that was probably the best analog on Earth for the kind of lava tubes that we would hope eventually to explore on Mars. And we didn't have a full-on ReachBot robot at that time. We had one arm. So we have one arm on a tripod. And I'll just show a little bit of the video. And this video actually, I think, is included as part of the media for the science robotics paper that describes this work. So as you can see, it's not fast. And we find a grasp, and then the gripper very slowly closes and tightens. And so we did targeting practice, we did pull force tests, and so on. And actually, we learned something from this. Even if things get faster, grasping at the end of a long boom is really pretty different from a robot grasping things on a tabletop. There's a level of commitment involved. It's not as severe as it would be for a drone perching, where you fly and you try to find a good perching spot, and either you land and grasp, or else you fall and you have to very hastily try to recover before you hit the ground and crash. You don't have that, but it takes a while to load these arms all the way out, and then you don't have very good targeting. In fact, we have to use endpoint sensing. We don't have very good control at the end of that very long arm. And so at that point, I've made a certain commitment that I really think that there ought to be something good to grasp out there. As I mentioned, we have both near and far scanning. And then, yeah, robustness, of course, is always an issue whenever you're doing anything in the field. Yeah, yeah. The one hanging down from the camera, or the very thin one going upward? Gravity compensation, because this thing's, Martian gravity is less than Earth. Yeah, so it's gravity offload.
I think say that for a rock climbing competition in such a case, would it make sense for me to try? You would give this to the professional rock climber,
Yeah.
give them finger cups with these needle surfaces.
Yeah.
What would they be able to excel with?
It's funny. We did talk to some rock climbers. Yeah, I mean, it is of use, because you can grasp with spines much faster than you can insert screws or things like that. So from that point of view, it should be good. And you can apply really large forces if the rock quality is good.
But because bulky in some way.
May do. Yeah, it's funny. Actually, the boom that we're now using on ReachBot, it's a 3-meter long boom. And one of the applications is for climbing that people use this. That's one of the things it's sold for. Yeah. So there's the concept. Now, I want to talk a little bit about some of the planning work of Marco's students, in particular, Stephanie. So there you are in your lava tube. One of the good things is that there's lots of handholds. And so now we're doing this kind of motion planning problem where I want to get from point A to point B. And I do that, I need to find a sequence of, it's basically two states. So we're doing a rather slow crawl where we move one arm at a time. And then within the constraints imposed by my kinematics and my limit surfaces, I can move the body a certain amount. And then I have to reposition an arm, and I just keep going. So that's how we move. And there have been a couple of papers on the motion planning problem here, but that's the gist of it. There's actually lots of handholds, and you want to get efficiently from one location to another, moving one boom at a time. Subject to constraints. There's the grass force constraint. There's a couple other things we learned. You want to keep all the booms in tension all the time. If you do that, the grasp is stiffer. And finally, you also want a stance that is resistant to perturbations. For example, if I'm, well, first of all, if there's a finite chance that a grasp will fail. So if a grasp suddenly fails, the force is a step function on that arm from something to 0. And depending upon how my other limbs are arranged, that could be catastrophic. I could fall, or I could undergo large oscillations, which would cause other grasps to fail, and so on. So part of a lot of the stance planning is adopting a sort of a conservative stance, such that if I would get a failure on any boom, it isn't going to cause a big problem. We presented this to NASA, and they said it's all very cool, but it seems kind of complicated and maybe expensive and heavy. And could you get away with fewer booms? And we said, yeah, let's think about that. So Stanley was a new student at Stanford. I challenged him on arrival to think about the absolute minimum number of booms, like, how about 1 boom? And then it becomes a cable-stayed robot. So you have a single boom that deploys a gripper, leaves the gripper there, and then comes back paying out a cable, and now you have a robot suspended by cables. So it's very slow, but in theory, you can do pretty much everything that you could do with the original ReachBot idea. So it turns out that there are some trade-offs, though, and this is new work with Dan Morton, who's working with Marco. And it has to do with how sensitive you are to suboptimal grasp choice. There we go. So on the left, I have a bunch of cables on a body of a robot, and on the right, I have also a bunch of cables, except I have a more kind of crossed configuration. And what you can see is that if you have a suboptimal, and then what I'm plotting here is essentially a polytope that corresponds to the quality of this cable-stayed grasp. If anybody is familiar with the Ferrari-Canny grasp algorithm, it's actually kind of similar. And the larger these things are, the better. And I've plotted it in a projection in 3 dimensions. And what you can see is that the cable one is noticeably slimmer. The ability to apply an arbitrary wrench and have it be sustained with the configuration on the left is not as good on the right. On the other hand, for the more optimal configuration, the cables are really nearly as good. So one of the main things we learned from this analysis is that yes, you could do a thing with some mixture of booms and cables, but the more you're suspended by cables, the more sensitive you are to a poorly chosen grasp. And as I thought about that, we've seen this kind of issue before. Where have we seen the difference between the picture on the left and the picture on the right? You see it every day. And what's the difference? Why is the one on the left? What in particular is better about the one on the right? Let's see, physical intuition here. Okay, I have an assignment for all the students, a short assignment, it's easy. On the way out from this seminar, take a hard look at the first bike rack that you find and look at the wheels on the bicycles and look at the difference in particular between the front wheel and the back wheel. And of course, if you really want to apply torque, as you often do on the rear wheel of especially a mountain bike, yeah, they always have these much more interlaced, crossed arrangements of the spokes because it allows you to apply more torque. Whereas the front wheel can, in extreme cases, be like the one on the left here. And that's exactly what you're seeing between those two pictures in the upper right corner. So does that make sense to you? Yeah. So amazingly, over Christmas, Stanley decided to build a prototype of this one-armed bandit ReachBot idea. It has a 2 degree of freedom gimbal. The boom itself is literally just 2 carpenter's tape measures back to back unspooling. And it can rotate into one of the different facets of this structure and grab a gripper. And I'll actually show you a little bit of the prototype here. And this is mainly a proof of concept. In the end, I don't actually think this is the direction. I mean, unless we're really, really on a very tight weight budget, I'm not sure that this is going to be my favorite design because it's quite slow. But you can see, well, let me actually, I forgot to mention, let me back up. So what did you see happen here? It came to life and it pivots and it's going to attach using a magnet, the gripper. And then it's pushing the gripper out and the gripper grabs onto a conveniently placed piece of lava and then it separates and retracts, but you can barely see it, but it's left as strings behind. And now it's a cable-stayed robot, at which point it can haul itself around within the confines of those cables, but it can always retract a gripper and put a new gripper somewhere else. So that's the basic idea. Well, in our current thinking, we're taking a sort of intermediate design. So we don't have, if you assume booms really are very long and they can only mainly be loaded in tension, then you ought to have 8 because you should have 6 plus 1. And then because you need to reposition booms one at a time, you should have 1 more. On the other hand, if you can apply modest but non-negligible torques at the shoulder, and you can apply some compression in the boom, then I only need 3 plus 1. And so that's the design we built for the open house of the Stanford Robotics Center. And by the way, you should all come to California and see the new Stanford Robotics Center. And if you do, you can play with this robot, which is set up there. And we started looking at other things like, wow, if these booms are really kind of sturdy, you know, maybe you could do other stuff. Maybe we could even do some locomotion. Like you could crawl along the floor of the lava tube to get to where you want to be before you start climbing. So these are things that we're interested in really right now. And one of the new students working on this, some of you may actually know Vinny, yeah? Because he was in our lab for a while. And then you start thinking about other things, like if these booms are actually kind of sturdy, and if I haven't really sent them way, way out there, maybe I could do some manipulation. At least I could have a 2-axis wrist and a gripper. And that opens up new possibilities. So it's interesting. I think we're moving from the concept of locomotion as manipulation, which is very much the original idea, to mobile manipulation, but with very, very long arms. And during, oh yeah, go ahead, Arnie. They have, yeah. You know, if I get time, I would like to propose to NSF a workshop on sort of interesting series parallel hybrid robots, which would include tensegrity robots, which would include ReachBot, which would include the sort of tetrahedral variations on the Vine robot, and a few other things that are out there, because they all have similar stance planning and motion planning characteristics. Yeah. Yeah. And then finally, we got some people from ANYMal were visiting, and we have one of the ANYMal robots, although I'm sad to say it's dead at the moment. We'll get it fixed. You know, what if you put a ReachBot arm on ANYMal? Is that possible? Sure. Actually, we have the dynamic simulation of ANYMal in Mujoko, and it actually handles it better than I thought it would. This is unpublished. This is just hot off the press as of like a week ago. But yeah, Stanley and another student have been doing some simulation. You know, ANYMal mostly walks with a fairly narrow stance, but it can take a wider stance. And if you do that, a boom with a 1 kilogram weight on the end is actually not as bad as I thought it would be. So we're doing these simulations right now, trying to make sure that the you know that the numbers are kind of correct. But yeah. So what could you do with this? We were talking to a guy, Paul Bingaman, who's involved with ANYMal, who there are locations for plant inspection and so on that it would really be nice to have an ANYMal that can go around. And then if there's, I don't know, well, let's say I need to fix something on that projector up there. No problem. I just extend my long arm and I can look around and I can maybe grab something or unplug something or whatever. So that's the kind of application that we have interest in. You could, although, I mean, you could balance. You could do dynamic balance. In fact, we already were asking, well, what, you know, ANYMal has this huge battery. Is there any reason I couldn't do like a construction crane and have the battery on the back? And we were told that we would rather you didn't make that level of modification just yet. But yes, 2 arms might not be much worse than 1 if you were clever about it. And we're thinking about that as well. It's a good idea, yeah. Oh, you could do other things. You know, with 2 arms, I'm strong enough maybe with my spines that if ANYMal came to a large gap, like between here and the other side of the balcony over there, that I could extend an arm up and swing. I mean, who knows what you could do? Yeah, but yeah. Okay, so that's where we are thinking right now. Because why? In part is because honestly, we're not going to go to Mars anytime super soon. And if you've read about the latest cutbacks at NASA, you know, 300 people laid off from JPL and so on, yeah. So the prospects for actually doing something with this technology are better for the commercial CLIPS program. There was finally a successful lander on the moon from a company. Actually, we earlier used to joke that the killer app for ReachBot was going to be writing toppled landers because there were 2 of them from previous attempts. So that's still there, although not super near term. And then what about terrestrial applications? And doing something with the combination of booms and ANYMal, I encourage you to think about that. And yeah, all right. So that is it for me. Thank you very much, and I'll take final questions. Yeah, please. With ReachBot, we haven't tried, and I actually don't think we would be able to because the gripper is not designed to be a good gripper for a flat wall. We're really banking on having that a little bit of the alpha, the wrap angle, in order to get a high ratio of pull force to internal force.
General curvature of the wall, like in a closed cave, or could you also just climb down a flat wall?
No, a cliff or something, yeah. As long as there are some features that have a radius of curvature that is kind of on the scale of the gripper, then it should work really well. So cliffs are also very much of interest. But for flat walls, you know, we've done that. That was RISE. It's a different solution because on the downside, it's flat, which means that internal forces are not as effective. But on the plus side, there's no features. So, you know, every place that you put a hand is just as good as anywhere else. Yeah.
Very gecko inspired, right?
The spines were, well, there's the backstory there is it was a DARPA project. And you know how DARPA, like 1 year, they want a dog and pony show. They want to see something exciting happening. And the gecko adhesives just were not ready at that time. So they said, yeah, well, we don't want catbot. And so then Bob Full, he said, well, what about cockroaches? What if it's a giant insect? Insects, cockroaches climb walls using spines. And so spines, we were able to get working at a practical level of carrying, a 10-kilogram robot much sooner than any of the gecko stuff. And it's interesting, in the end, a lot of the principles are very similar. This paramount importance of load sharing, so that if that we found this with the gecko adhesives too. You can't just make the adhesive area bigger and bigger, or the maximum pressure goes way down. You have to do load sharing. And that was Elliot's work, finding ways to do that. So yeah, you're right. Elliot?
Yeah. Years ago.
Oh, okay. I didn't know that. Yeah. Yeah, he is a biker. Yeah, well, you can imagine that putting spines on your racing bike was something that would occur to him. Yeah. Yeah. That's a good point. I didn't get into that, but that's something else we're exploring. So booms are made for a couple of reasons. The ones for space are very strong and very light, and they have a closed cross section. Now, the problem with that is that when you flatten them and put them on a roll, you really get quite high stresses. So they are usually made to deploy just once or twice. And there's actually some work at MIT and elsewhere on, fatigue and all that. We're using booms that are, I'm willing to trade off some of that weight and stiffness in order to have something that I can deploy many, many times. So the ones we're using are, they're like a fiberglass, I think, composite, and the matrix material is probably a urethane rather than an epoxy. They're a little heavier than I would like. They're a C shape. So because it's an open cross section, they're not nearly as stiff in torsion. We've thought about ways of closing it. Don't have anything to show yet. And eventually, we may have to make our own booms, although that's a complicated process. You need to autoclave a really long structure. But fortunately, we've got another new faculty member at Stanford, Maria Cutkosky, who's also an expert in the space structures. So it could be an option in the future. For now, these 3-meter long ones are what we're using, and they're certainly okay to work on lots of other interesting problems like grasping and motion planning and so on. Yeah.
How much increased torsion and stiffness would increase the manipulation and locomotion?
It does. I mean, right now for manipulation, it's a funny manipulation problem because now you've got a robot where I can apply fairly large torques this way without a problem, but not this way because the whole thing just twists. So makes an interesting problem for a student to work on, but but it's also practical. Yeah. So no, if they would be a closed tube, that really would be better. Yeah. And there was a couple in the back. Yeah. Questions? I think he was first and then you. Yeah. We haven't done anything in hardware between ReachBot and ANYMal yet because we're still waiting to get our replacement battery for ANYMal. But in simulation, we're starting to explore these things. It is soon. It'll happen soon. Yeah. And then you had a question too.
Test about the flatness or roughness of the surface and how
Yeah.
scale. Is there any test that you have or kind of thing that you have noticed when the walls are the surface is not is soft and not hard? For example, you presented rocks, but some surfaces are more like sandy.
Well, like bark or something of a tree. Yeah. So penetration actually is good that I can apply larger forces. If the surface is friable, like Adobe, we actually did a version of a gripper years ago for Adobe walls, and we had to have many, many, many very small spines because then the failure of the wall itself was the limiting factor. Yeah.
there actually makes sense.
Yeah,
Then it doesn't fail.
yeah, no, you're right.
Ungrass. Intuitively, I think this would be much harder.
No, it's not actually. As soon as we relax the load, because we have that compliance, everything kind of extends a little bit and it pops right off. And then we have another tendon that pulls it back. So actually detaching is very easy. And when you're climbing a wall with spines, it's almost horrifyingly easy. Yeah. Mhm. Yes, that was us. That was with Dario Floriano at APFL, Lycrotugs. Yeah, no, what it was is a drone. This was with Matt Estrada, who graduated with me and then did a postdoc with Dario. You have a drone that flies and it has a spine gripper that it detaches and leaves latched onto a surface. And then it can either fly or crawl away while paying out a string and anchor itself. And now it can pull quite hard. Yeah.
Is there any more questions on Zoom maybe? No?
Yeah, good question. So,
Maybe.
oh, Arden, yeah, sure.
Should there be an intra track on manipulation?
Locomotion by manipulation. Yeah, well, there certainly could be, or a workshop or something. Yeah, I mean, I think it would be fun to organize that. And yeah, you could do. Yeah, interesting idea. You know, the other domain, Arden, where you will see in biology solutions a bit like this is underwater near the coast, liminal, because you have these huge water currents, you know, from waves and so on. So if you look at lobsters and crabs that need to anchor themselves to the substrate and also locomote. Yeah. And also they don't have to worry about gravity so much. So, yeah.
Okay, so if there is no more questions, then thank you, Mark,
Yeah, sure.
for this inspiring talk, and let's give him a round of applause.